The outer darkness holds secrets we're only beginning to understand. While the world focused on the mysterious visitor 3I Atlas that swept through our solar system, astronomers discovered something far more disturbing lurking in the frozen depths beyond Neptune. It's called Bernardinelli-Bernstein, and everything about this colossal object challenges what we thought we knew about the structure of our cosmic neighbourhood. At first glance, you might dismiss it as just another comet. After all, we've catalogued thousands of these icy wanderers over the centuries. But Bernardinelli-Bernstein isn't just another chunk of frozen debris. This is a monster that dwarfs every interstellar visitor we've encountered. Where 3I Atlas measured perhaps a few hundred meters across, Bernardinelli-Bernstein stretches an incredible 137 kilometers in diameter. To put that in perspective, this single object contains roughly 10,000 times more mass than 3I Atlas ever did. The discovery itself reads like a detective story. In 2014, buried deep within archival images from the Dark Energy Survey, astronomers spotted what appeared to be an ordinary moving object. Space surveys capture millions of these detections every year, so initially nobody paid much attention. But as researchers began tracking this particular dot of light, measuring its motion and analysing its characteristics, something became unmistakably clear. This wasn't ordinary at all. When the measurements finally came back from the Hubble Space Telescope, the numbers were staggering. The nucleus alone spans roughly 85 miles across, making it more like a dwarf planet masquerading as a comet than anything we've seen before. Most comets in our catalogues measure just a few kilometers in width. Bernardinelli-Bernstein is so massive that it challenges our fundamental understanding of how these objects form and survive. But size is only the beginning of what makes this object so unsettling. Unlike the small, fragile visitors we're accustomed to studying, Bernardinelli-Bernstein has been part of our solar system for billions of years. It originated not from another star system, but from the Oort cloud, that vast spherical shell of icy debris that surrounds our Sun at unimaginable distances. For eons it has lurked in the frozen darkness, roughly 1 light-year from the warmth of our star. And now, after spending billions of years in that cosmic deep freeze, it's falling inward. The implications of this inward journey are profound. Bernardinelli-Bernstein isn't moving like 3I Atlas did, racing through our solar system on a hyperbolic trajectory before disappearing forever into interstellar space. Instead, this giant is bound to our Sun, following an elliptical orbit that will bring it steadily closer over the coming years. Its destination is a point just beyond Saturn's orbit, where it will reach perihelion in January 2031. What makes this approach particularly fascinating is how early the object began showing signs of activity. Most comets remain dormant until they venture relatively close to the Sun, where solar heating can vaporize their surface ices. But Bernardinelli-Bernstein started brightening years ago, way out beyond Neptune, where the Sun's warmth is barely a whisper. At that distance, water ice simply cannot sublimate. Something else must be driving this activity. The answer came from the Atacama Large Millimeter Array in Chile. In 2024, this sophisticated radio telescope network detected powerful jets of carbon monoxide erupting from specific regions on the comet's surface. This was happening at approximately 16.6 astronomical units from the Sun, far beyond where most comets show any signs of life. For reference, Saturn orbits at roughly 9.5 astronomical units. Bernardinelli-Bernstein was already active in the deep cold of the outer solar system. Carbon monoxide is what astronomers call a hypervolatile substance. It sublimates at incredibly low temperatures, much lower than water ice. The fact that Bernardinelli-Bernstein possesses enough carbon monoxide to produce visible jets at such distances means its interior harbours massive reservoirs of this gas, preserved for billions of years in the frigid depths of the Oort cloud. Most comets lose their carbon monoxide early in their evolutionary history, as this volatile substance vents away into space. But not Bernardinelli-Bernstein. This object has remained cold enough for long enough to preserve enormous quantities of carbon monoxide deep within its structure. This discovery thrilled mainstream astronomers, who immediately recognized its significance. Here was a pristine sample from the early solar system, a relic from the era when planets were still forming. By studying Bernardinelli-Bernstein, they argued, we could examine the raw materials that built the worlds we know today. The scientific community hailed it as an unprecedented opportunity to peer back in time, to understand the chemical and physical processes that shaped our cosmic neighborhood billions of years ago. But beneath the excitement, uncomfortable questions began to emerge, questions that some scientists found difficult to answer with conventional explanations. The most pressing question was simple yet profound. Why now? If Bernardinelli-Bernstein had been sitting peacefully in the Oort cloud for over 4 billion years, what suddenly disturbed its orbit? What force was powerful enough to nudge this massive object out of its stable configuration and send it tumbling toward the inner solar system? The Oort cloud extends from roughly 2,000 astronomical units to perhaps 100,000 astronomical units or more from the Sun. At those distances, our star appears as nothing more than a bright point of light among many others. Gravitational forces are incredibly weak. Objects drift through this region on timescales measured in millions of years, and under normal circumstances they should remain there indefinitely unless something significant disturbs them. Several hypotheses emerged to explain Bernardinelli-Bernstein's sudden journey inward. Some researchers proposed galactic tides as the culprit. Our solar system doesn't exist in isolation but orbits within the Milky Way galaxy, encountering gravitational influences from countless stars, gas clouds, and concentrations of dark matter. These forces create tidal effects that oscillate and pulse as we move through galactic space. Some dynamicists believe these pulses can perturb Oort cloud objects, gradually nudging them from stable orbits toward eventual infall. There's even a specific model gaining attention in research circles, a 14,400-year tidal pulse scenario. This hypothesis suggests that every 14,400 years or so, a particularly strong galactic tide sweeps through the outer Oort cloud. Objects at the very edge of this region feel the tidal pull most strongly. Over time, their orbits change slowly and gradually, until one day they're no longer stable. They begin falling inward, starting a journey that may take millions of years to complete. Other scientists favor the passing star hypothesis. Stellar motions through the galaxy bring stars near each other on regular intervals. Millions of years ago, another star may have drifted through the outer reaches of the Oort cloud. Even at distances of several thousand astronomical units, such an encounter could gravitationally perturb distant comets. The European Space Agency's Gaia mission has been mapping stellar motions across our local galactic neighborhood, and some researchers have used this data to suggest that a star did indeed pass near our solar system in the distant past. These gravitational encounters don't need to be dramatically close to have significant effects. Even a star passing several thousand astronomical units away can exert enough differential force to alter the orbits of Oort cloud objects. The changes are small and incremental, but over geological timescales, they accumulate. An object's orbital eccentricity increases, its trajectory shifts, and eventually it begins the long fall toward the inner solar system. If either of these scenarios explains Bernardinelli-Bernstein's journey, they carry disturbing implications. The Oort cloud contains an estimated 1 trillion icy bodies, ranging from small fragments to objects as large as Bernardinelli-Bernstein itself. If galactic tides or stellar encounters can shake these objects loose from their distant orbits, then Bernardinelli-Bernstein represents just the beginning. Many more objects should be en route, following similar trajectories inward. But there's a third possibility that makes some researchers deeply uncomfortable. What if neither galactic tides nor passing stars can fully account for Bernardinelli-Bernstein's motion? What if there's something else out there, something we haven't detected yet, that's been quietly perturbing Oort cloud objects for eons? This leads to whispered discussions about hidden influences. Perhaps a massive object lurks beyond the Oort cloud, too distant and faint for our telescopes to detect. It could be a rogue planet, ejected from its original star system billions of years ago and now drifting through interstellar space. Or it might be a concentration of dark matter, that mysterious substance that comprises most of the universe's mass, but interacts only through gravity. Some theorists even propose more exotic possibilities. What if there's a primordial black hole in the outer reaches of our solar system? These hypothetical objects, formed in the first fraction of a second after the Big Bang, could have the mass of several Earth-sized planets compressed into a region smaller than a city. Such an object would be virtually impossible to detect directly, but its gravitational influence would be unmistakable over cosmic timescales. The mathematics of orbital mechanics are unforgiving. When researchers try to model Bernardinelli-Bernstein's trajectory backwards through time, tracing its path to determine what could have set it in motion, they find that natural explanations require very specific conditions. The probabilities are uncomfortably low. Either we've been extraordinarily unlucky, or there are forces at work that we don't fully understand. What makes this uncertainty particularly troubling is the object's orbital characteristics. Bernardinelli-Bernstein isn't following a simple, predictable path through the solar system. Its orbit is inclined at nearly 95 degrees relative to the plane where the planets orbit. This means it's approaching from almost directly above the solar system, cutting down through the ecliptic plane like a massive bullet fired from the galactic north. Such extreme orbital inclinations don't occur by accident. They're signatures of violent gravitational interactions, evidence that something powerful enough to completely reshape an object's trajectory acted upon it in the distant past. The question is what that something was, and whether it might still be out there, influencing other objects we haven't yet discovered. As Bernardinelli-Bernstein continues its slow approach toward the inner solar system, these questions become increasingly urgent. Because if we don't understand what set this giant in motion, how can we predict what else might be coming? How many more massive objects are currently falling inward from the Oort cloud, their approach still hidden by distance and darkness? The answer to that question may determine not just our understanding of solar system dynamics, but our ability to prepare for what could be the most spectacular astronomical event of our lifetimes. Because when Bernardinelli-Bernstein finally reaches its closest approach to the Sun, the transformation it undergoes may reveal secrets about the formation of our cosmic neighbourhood that have remained hidden for over 4 billion years. But first, we need to understand exactly what this object is and why its internal structure suggests it might be something far more complex than any comet we've studied before. When scientists first began studying Bernardinelli-Bernstein's internal composition, they expected to find the familiar signature of a typical comet, a loose collection of ice, dust, and rocky debris held together by weak gravitational forces. What they discovered instead challenged every assumption about how objects of this size should behave in the outer solar system. The Hubble Space Telescope's detailed observations revealed something unprecedented. Unlike the irregular, potato-shaped nuclei that characterize most comets, Bernardinelli-Bernstein appears remarkably spherical. This geometric perfection isn't accidental. It's the signature of an object massive enough to pull itself into a sphere through its own gravitational field, a process called hydrostatic equilibrium that typically occurs only in planets and large moons. For a comet to achieve this level of structural organization requires internal forces that go far beyond simple gravitational binding. The spherical shape suggests that heavier materials may have migrated toward the center over billions of years, while lighter compounds rose toward the surface. This process, known as differentiation, transforms a chaotic mixture of primordial debris into a layered, organized body with distinct internal zones. The implications are staggering. If Bernardinelli-Bernstein has undergone differentiation, it's not really a comet in the traditional sense. It's more like a dwarf planet that happens to be venting gas as it approaches the Sun. This would place it in an entirely different category of solar system objects, one that bridges the gap between the small, primitive comets we're familiar with and the larger, more evolved bodies that populate the outer solar system. Radio observations from the Atacama Large Millimeter Array added another layer to this puzzle. The carbon monoxide jets weren't emerging randomly from the surface. Instead, they appeared to originate from specific persistent regions, suggesting an organized internal structure with distinct reservoirs of volatile materials. These aren't the chaotic outbursts typical of small comets, but rather controlled releases from what appears to be a complex internal architecture. The persistence of these jets over multiple observation periods indicates something even more remarkable. Most comets exhaust their volatile reserves relatively quickly, their activity declining as they lose material to space. But Bernardinelli-Bernstein continues to vent carbon monoxide at consistent rates, suggesting it possesses vast internal stores of this hypervolatile compound. The quantities required to sustain such activity over extended periods would dwarf anything we've seen in conventional comets. Some researchers propose that Bernardinelli-Bernstein may contain a stratified interior with different volatile compounds frozen at various depths. The outermost layers might consist of relatively stable water ice mixed with rocky debris. Beneath that, Reservoirs of carbon dioxide ice could wait in the cold darkness. Deeper still, pockets of pure carbon monoxide might remain preserved from the solar system's earliest days. As the object approaches the Sun, these layers would heat up sequentially. First, the carbon monoxide begins to sublimate, creating the jets we observe today. Later, as temperatures rise, carbon dioxide would start to vent. Finally, if the object ventures close enough, water ice would begin to sublimate, potentially creating a spectacular coma and tail visible from Earth. This layered structure could explain another puzzling observation. Thermal models of Bernardinelli-Bernstein's approach suggest it should be heating up more rapidly than it actually is. Something appears to be regulating its temperature, preventing the runaway heating that typically characterizes comets as they near the Sun. If the object possesses an organized internal structure with efficient heat distribution mechanisms, it could maintain thermal stability far longer than a simple pile of debris. The gravitational data presents yet another mystery. When astronomers calculated the object's mass based on its observed motion and gravitational effects, they found it was far denser than typical comet nuclei. Most comets have densities comparable to loosely packed snow, reflecting their origin as aggregations of primitive dust and ice. Bernardinelli-Bernstein appears much more compact, suggesting either a different formation mechanism or significant internal processing over geological time. This density anomaly raises uncomfortable questions about the object's true nature. If it formed through the same processes that created other Oort cloud objects, why is it so much denser and more organized? The most likely explanation is that Bernardinelli-Bernstein began its existence not as a comet, but as something much larger and more complex. During the chaotic early period of solar system formation, when planets were still assembling from countless smaller building blocks, many objects achieved significant size before being ejected to the outer reaches of the system. These protoplanets experienced internal heating from radioactive decay and gravitational compression, allowing them to begin the differentiation process before being frozen in the depths of the Oort cloud. If this scenario is correct, Bernardinelli-Bernstein represents a unique opportunity to study a planetary embryo that was preserved in its formative state for over 4 billion years. Unlike the planets in our inner solar system, which continued evolving and processing their internal materials, this object was flash-frozen at a crucial moment in its development. Studying its composition and structure could reveal details about planetary formation that have been erased everywhere else in the solar system. But there's another possibility that makes some researchers deeply uncomfortable. What if Bernardinelli-Bernstein's organized structure isn't the result of natural geological processes, but something else entirely? The object's unusual properties, its perfect spherical shape, its persistent and organized outgassing, and its anomalous density all point toward a level of internal organization that seems almost engineered. This speculation remains firmly in the realm of fringe science. There's no credible evidence suggesting artificial origin for Bernardinelli-Bernstein. Every observation can be explained, albeit with some difficulty, through natural processes operating over cosmic timescales. Yet the combination of anomalous properties continues to generate quiet discussion in certain research circles. The thermal behavior presents perhaps the most intriguing puzzle. As Bernardinelli-Bernstein approaches the Sun, its surface temperature should rise predictably according to well-established physical laws. Instead, the object appears to be maintaining thermal equilibrium through some kind of internal regulation. Heat absorbed on the sun-facing hemisphere somehow gets redistributed throughout the interior, preventing the thermal runaway that destroys most comets at similar distances. This kind of thermal management requires either exotic internal composition or organized internal structure. Natural materials rarely exhibit such precise temperature control without active mechanisms. If the object contains metallic components or unusual crystalline structures, these might provide pathways for efficient heat distribution. Alternatively, the organized internal architecture suggested by the persistent outgassing patterns might create convection systems that transport heat throughout the interior. Spectroscopic analysis of the carbon monoxide jets reveals another anomaly. The gas appears unusually pure, lacking the contamination from other compounds that typically accompanies cometary outgassing. This suggests either remarkably efficient separation mechanisms within the interior or storage systems that have maintained chemical purity over billions of years. Neither explanation fits comfortably within our understanding of how natural objects evolve in the outer solar system. As Bernardinelli-Bernstein continues its approach toward perihelion, these internal mysteries will become increasingly important. The object's response to solar heating will reveal crucial information about its structure and composition. If it behaves like a typical comet, fragmenting or dramatically increasing its activity as temperatures rise, then natural explanations will gain credibility. But if it continues to exhibit the organized, controlled behavior observed so far, it will force us to reconsider fundamental assumptions about what's possible in the outer solar system. The stakes of this observation campaign extend far beyond academic curiosity. If Bernardinelli-Bernstein represents a new class of objects lurking in the Oort cloud, our understanding of the outer solar system's structure and dynamics requires complete revision. The implications for planetary defense, for future exploration missions, and for our basic comprehension of how planetary systems evolve would be profound. But before we can fully appreciate these implications, we need to understand another disturbing aspect of Bernardinelli-Bernstein's journey, the possibility that it's not alone. Recent observations suggest this massive object may be part of a larger pattern, a clustering of unusual visitors that challenges our assumptions about the random nature of Oort cloud dynamics. The clustering phenomenon that emerged in late 2024 sent shockwaves through astronomical research facilities worldwide. Within a span of just 8 years, our detection systems had identified an unprecedented number of unusual objects entering or passing through our solar neighborhood. The statistical probability of such a concentration occurring naturally was so low that it forced scientists to confront an uncomfortable reality. Something systematic might be happening in the outer reaches of our cosmic domain. The sequence began in October 2017 with the detection of Oumuamua, the first confirmed interstellar object ever observed passing through our solar system. This elongated, tumbling visitor exhibited behavior that defied easy categorization. It showed no visible coma or jets typical of comets, yet its trajectory bent slightly as it passed the Sun, suggesting some form of outgassing or external force. Scientists spent months debating its true nature, with theories ranging from an unusual asteroid to something far more exotic. Just 2 years later, in August 2019, another interstellar visitor arrived. Designated 2I Borisov, this object displayed all the characteristics astronomers expected from a comet originating beyond our solar system. It possessed a visible coma, exhibited clear gas jets, and spectroscopic analysis revealed familiar molecules including carbon monoxide, water, and cyanogen. Borisov's conventional behavior provided some reassurance that cometary physics operated consistently across interstellar space. The arrival of 3I Atlas in 2025 added another data point to this emerging pattern. Though smaller and less well studied than its predecessors, this object followed the expected trajectory of an interstellar visitor, racing through our solar system at tremendous velocity before disappearing back into the cosmic void. 3 interstellar objects in less than a decade represented a detection rate that exceeded theoretical predictions. Now Bernardinelli-Bernstein adds weight to this clustering, though its origin story differs fundamentally from the interstellar visitors. Unlike the hyperbolic trajectories that carried Oumuamua, Borisov, and 3I Atlas through our system, Bernardinelli-Bernstein follows an elliptical orbit that marks it as a long-term resident of our solar neighborhood. Yet its massive size, unusual composition, and anomalous behavior place it firmly in the category of objects that challenge conventional understanding. The observational bias argument suggests a mundane explanation for this apparent surge in detections. Our telescopes have improved dramatically over the past decade. Survey programs scan larger portions of the sky with greater sensitivity than ever before. Automated detection algorithms can identify moving objects with unprecedented efficiency. From this perspective, we're simply finding more objects because we're looking harder and with better tools. But when dynamicists ran the statistical analysis, the numbers didn't align perfectly with observational improvements alone. The detection rate for unusual objects exceeded what telescope improvements should have produced. The margin wasn't enormous, but it was significant enough to suggest that something beyond observational bias might be occurring. This led to the development of what researchers quietly term the perturbation pulse hypothesis. If some external force had disturbed the Oort cloud in the relatively recent past, astronomically speaking, It could have sent multiple objects on inward trajectories with staggered arrival times. The objects we're detecting now might represent the leading edge of a much larger wave of material displaced from the outer solar system millions of years ago. The hypothesis gained credibility when researchers began analysing the orbital characteristics of known long-period comets, objects that originated in the Oort cloud and fell inward over geological timescales. Instead of random arrival patterns, subtle periodicities began to emerge from the data. The intervals weren't precise or easily predictable, but they suggested waves of activity separated by millions of years. These patterns matched theoretical work from previous decades that had proposed galactic influences on Oort cloud dynamics. As our solar system orbits through the Milky Way, it encounters varying gravitational environments, spiral arm passages, interactions with giant molecular clouds, and tidal forces from the galaxy's central bulge all create periodic disturbances that could shake loose material from the outer reaches of our planetary system. The implications of this clustering extend far beyond academic interest in solar system dynamics. If Bernardinelli-Bernstein represents part of a larger influx of Oort cloud material, then multiple massive objects could be approaching the inner solar system simultaneously. Our current detection systems, impressive as they are, can only identify objects that have approached close enough to reflect sufficient sunlight or begun outgassing at detectable levels. The search for additional cluster members has intensified dramatically since Bernardinelli-Bernstein's unusual properties became apparent. Deep sky surveys are being reanalyzed with new algorithms designed to identify faint, slowly moving objects in the outer solar system. The computational requirements are enormous, as these searches must examine years of archival data, looking for motion patterns that could indicate massive objects still too distant to characterize in detail. Preliminary results from these searches have identified several candidate objects that warrant further investigation. None approach Bernardinelli-Bernstein's tremendous size, but several show motion patterns consistent with large bodies falling inward from the Oort cloud. The confirmation process is painstaking, requiring months or years of follow-up observations to establish definitive orbits and physical characteristics. The gravitational modelling of multiple massive objects approaching simultaneously presents unprecedented challenges for orbital prediction systems. Each object influences the others through gravitational interactions, creating a complex web of forces that evolve continuously as the objects move through the outer solar system. Traditional two-body orbital mechanics, which work perfectly for isolated objects, become inadequate when dealing with multiple massive bodies in relatively close proximity. Computer simulations attempting to model these interactions require enormous computational resources and sophisticated algorithms. The calculations must account not only for gravitational forces between the objects themselves, but also their interactions with the known planets, particularly the gas giants, whose massive gravitational fields can significantly alter trajectories of objects passing through the outer solar system. What makes these simulations particularly challenging is the uncertainty inherent in the initial conditions. We don't know the precise masses, compositions, or internal structures of most candidate objects. Small variations in these parameters can lead to dramatically different evolutionary paths over the timescales involved in Oort cloud dynamics. The clustering hypothesis has also revived interest in searches for the hypothetical Planet 9, a proposed massive object in the outer solar system that could explain certain orbital anomalies among trans-Neptunian objects. If such a planet exists, its gravitational influence could be responsible for perturbing Oort cloud material and sending objects like Bernardinelli-Bernstein on inward trajectories. Despite years of intensive searching, Planet 9 remains elusive. The predicted region where it should reside has been surveyed repeatedly with increasingly sensitive instruments, yet no definitive detection has emerged. Some researchers argue that the orbital clustering originally attributed to Planet 9 might be statistical artifacts or observational biases rather than evidence for a hidden massive world. Alternative explanations for the perturbation source include transient gravitational influences from passing stellar systems or interactions with dense concentrations of dark matter. The local galactic environment contains structures and phenomena that operate on scales far larger than individual planetary systems, and their effects on Oort cloud dynamics remain poorly understood. Recent advances in gravitational wave astronomy have opened new possibilities for detecting massive objects through their gravitational signatures rather than electromagnetic emissions. If Planet 9 or another massive perturber exists in the outer solar system, future gravitational wave detectors might be sensitive enough to identify its presence through the tiny space-time distortions it creates. The search for clustering patterns has also benefited from machine learning algorithms capable of analyzing vast datasets for subtle correlations that might escape human attention. These systems can identify orbital resonances, timing coincidences, and trajectory alignments that suggest common origins or shared perturbation events. One particularly intriguing correlation emerged from analysis of the arrival directions of unusual objects. Rather than approaching from random directions across the sky, several objects, including Bernardinelli-Bernstein, show arrival vectors that cluster within specific regions of space. This could indicate that the perturbation source influenced objects preferentially from certain directions, creating a directional bias in the resulting trajectories. The clustering analysis has also revealed temporal patterns that extend beyond the recent influx of unusual objects. Historical records of bright comets and unusual celestial phenomena show similar periodicities when analysed over centuries or millennia. These patterns suggest that the current wave of activity might be part of a much longer cycle of Oort cloud disturbances. Archaeological and geological evidence for past impact events on Earth and other planetary bodies also shows periodic clustering, though the timescales involved make direct correlation with astronomical observations challenging. If the same forces that are currently sending objects like Bernardinelli-Bernstein inward have operated throughout solar system history, they might have played crucial roles in shaping planetary evolution through repeated bombardment episodes. The implications for planetary defense are sobering. Current detection and tracking systems are optimized for identifying potentially hazardous asteroids and comets that might threaten Earth within the next century. But if multiple massive objects are approaching from the Oort cloud simultaneously, the timeline for detection and characterization becomes much more compressed. Unlike asteroids in the inner solar system, which can be tracked for years or decades before potential impact, Oort cloud objects might not become detectable until they've already begun their final approach toward the inner planets. The lead time for any defensive measures would be measured in years rather than decades, severely limiting our options for response. The clustering phenomenon has forced a fundamental reassessment of how we monitor and understand our cosmic neighborhood. The comfortable assumption that the outer solar system remains stable over human timescales has given way to recognition that we inhabit a dynamic environment, subject to forces operating on scales we're only beginning to comprehend. As observation campaigns continue and more data accumulates, the true scope of the clustering phenomenon will become clearer. Whether Bernardinelli-Bernstein represents an isolated anomaly or the herald of a much larger wave of activity remains to be determined. But one thing has become undeniable. Our solar system is far more active and unpredictable than we ever imagined. The race to understand these patterns intensifies with each new detection, because if the clustering hypothesis proves correct, what we're witnessing now may be just the beginning of a much larger cosmic event that could reshape our understanding of planetary system dynamics forever. The sheer scale of what we're potentially facing becomes clearer when you examine the mathematics of Oort cloud dynamics. Traditional models assumed this vast spherical shell of icy debris remained relatively stable, with only occasional objects falling inward due to random gravitational perturbations. But if external forces are systematically disturbing this region, the number of objects currently en route toward the inner solar system could be staggering. Consider the implications. The Oort cloud contains an estimated trillion objects, ranging from small fragments to giants like Bernardinelli-Bernstein. If even a tiny fraction of this population has been displaced by whatever force initiated the current clustering phenomenon, we could be looking at hundreds or thousands of objects currently making the long journey inward. Most would be too small and distant to detect with current technology, but some could rival or exceed Bernardinelli-Bernstein in size and destructive potential. The detection challenge is formidable. Unlike asteroids in the inner solar system, which reflect sunlight and can be spotted years or decades before potential impact, Oort cloud objects remain essentially invisible until they begin outgassing or approach close enough to reflect detectable amounts of solar radiation. By the time we identify these giants, they may be less than a decade away from their closest approach to the Sun. This compressed timeline has profound implications for scientific study and potential defensive measures. The window for detailed characterization becomes critically narrow. Where we might have decades to study an approaching asteroid, massive comets from the Oort cloud could transition from unknown to active to departing within just a few years of detection. The orbital mechanics involved create additional complications. Objects approaching from the Oort cloud follow highly elliptical trajectories that bring them racing through the outer solar system at tremendous velocities. Unlike the predictable orbits of inner system objects, these paths can be significantly altered by gravitational encounters with the giant planets, making long-term trajectory prediction extremely challenging. Jupiter, with its immense gravitational field, acts as a cosmic billiard ball, capable of dramatically altering the paths of incoming objects. An Oort cloud visitor that appears headed for a safe passage beyond Saturn could be redirected toward the inner planets by a close encounter with Jupiter. Conversely, objects on potentially dangerous trajectories might be deflected harmlessly outward. These gravitational interactions operate on such scales that tiny variations in initial conditions can produce vastly different outcomes. The famous butterfly effect of chaos theory applies directly to orbital mechanics in the outer solar system. An object's trajectory millions of years from now depends sensitively on its exact position and velocity today, parameters we can measure only with limited precision. The computer modeling required to predict these interactions pushes current computational capabilities to their limits. Simulating the gravitational dance of multiple massive objects moving through the gravitational fields of the known planets requires enormous processing power and sophisticated algorithms. Even then, the inherent chaos in the system means that long-term predictions carry substantial uncertainty. Recent advances in artificial intelligence and machine learning offer new approaches to these computational challenges. Neural networks trained on vast datasets of orbital mechanics can identify patterns and correlations that escape traditional analysis methods. These systems excel at finding subtle relationships in complex high-dimensional data, potentially revealing organizational principles underlying the apparent chaos of Oort cloud dynamics. Early results from AI-assisted analysis have identified intriguing correlations between the orbital parameters of incoming objects and the large-scale structure of our local galactic environment. The directions from which objects approach, their orbital inclinations, and their timing all show statistical patterns that suggest systematic rather than random influences. These patterns point toward external forces operating on scales far larger than individual planetary systems. The motion of our entire solar system through the Milky Way galaxy exposes us to varying gravitational environments as we encounter spiral arms, molecular clouds, and concentrations of dark matter. Each passage through these structures creates tidal forces that can penetrate deep into the Oort cloud, gradually reshaping the orbits of distant objects. The galactic year, the time required for our solar system to complete one orbit around the Milky Way center, spans roughly 225 million Earth years. During this cosmic circuit, we experience different gravitational influences as we move through varying galactic neighborhoods. Dense stellar regions, sparse intergalactic zones, and the complex gravitational architecture of spiral arms all leave their mark on Oort cloud dynamics. Some researchers propose that we may currently be experiencing the after-effects of a passage through a particularly dense region of the galaxy that occurred millions of years ago. The gravitational disturbances from that encounter could have set vast numbers of Oort cloud objects on slow trajectories toward the inner solar system, with different objects taking varying amounts of time to complete their inward journey based on their initial distances and orbital characteristics. This scenario would explain both the clustering of unusual objects and the diversity in their arrival times and trajectories. Objects displaced from different regions of the Oort cloud would follow distinct evolutionary paths, arriving at different times, but all sharing a common origin in the same ancient perturbation event. The evidence supporting this galactic influence hypothesis comes from multiple sources. Studies of stellar motion in our local galactic neighborhood reveal that our solar system has indeed encountered regions of enhanced stellar density within the past several million years. These encounters would have subjected the Oort cloud to gravitational stresses significantly stronger than the background galactic tidal field. Geological evidence from Earth also supports periodic bombardment episodes that correlate with our solar system's galactic orbital motion. Impact craters, mass extinction events, and geochemical anomalies in the rock record show clustering patterns that match the expected timing of galactic plane crossings and spiral arm encounters. The most recent of these galactic encounters may have occurred roughly 2 to 3 million years ago, when our solar system passed through a region of space containing multiple massive stellar systems. The gravitational chaos of such an environment would have sent shockwaves through the Oort cloud, displacing objects across a wide range of distances and setting them on trajectories that are only now bringing them into the observable region of the solar system. If this timeline is correct, we may be witnessing the beginning of a bombardment episode that could continue for several million years. The objects we're detecting now, including Bernardinelli-Bernstein, would represent the fastest moving members of a much larger population still making its way inward from the Oort cloud's depths. The implications extend beyond our solar system. If galactic influences regularly disrupt planetary system architecture, then every star in the galaxy periodically experiences similar episodes of enhanced cometary activity. The frequency and intensity of these events would depend on each system's galactic orbit and the local stellar environment it encounters. For planetary systems in dense stellar regions, such disruptions might occur frequently enough to prevent the development of stable, long-term biospheres. Conversely, systems in galactic backwaters might experience bombardment episodes so rarely that they provide ideal conditions for biological evolution over geological timescales. Our solar system appears to occupy an intermediate position, experiencing periodic disruption, but with sufficient quiet intervals to allow complex life to develop and flourish. The current influx of Oort cloud material might represent a natural cycle that has repeated throughout Earth's history, sometimes causing mass extinctions, but also potentially delivering the organic compounds and water necessary for life's continued evolution. The search for additional cluster members continues with increasing urgency as researchers recognize the potential scope of what we might be facing. Advanced detection algorithms scour archival data from sky surveys, looking for the subtle motion signatures that could reveal massive objects still years away from becoming easily observable. These searches require enormous computational resources and sophisticated statistical techniques to distinguish genuine moving objects from instrumental artifacts, stellar proper motion, and other sources of apparent motion in astronomical images. The challenge becomes even more complex when searching for objects at the extreme distances where Oort cloud material first becomes detectable. Machine learning algorithms trained on known comet detection data are being adapted to identify the specific patterns associated with very distant, slowly moving objects. These systems must learn to recognize motion signatures that might span multiple years of observations, while filtering out the countless false positives generated by statistical noise in the data. The international cooperation required for this search effort has led to unprecedented coordination between observatories and space agencies worldwide. Ground-based telescopes in both hemispheres contribute observations, while space-based assets provide the stable, long-term monitoring necessary to track objects over the multi-year intervals required to establish definitive orbits. Private observatories and amateur astronomers also play crucial roles in this expanded search effort. The distributed nature of modern astronomy means that important discoveries can come from unexpected sources, and the sheer volume of data being collected requires contributions from observers at every level of sophistication. The economic implications of the enhanced search effort are substantial. Telescope time is expensive, and the computational resources required for data analysis represent significant ongoing costs. But the potential consequences of missing a massive incoming object far outweigh these expenses, driving continued investment in detection and characterization capabilities. As the search continues and more data accumulates, the true scope of the clustering phenomenon becomes clearer. Whether we're experiencing a routine galactic perturbation episode or something more unusual remains to be determined. But the mounting evidence suggests that our cosmic neighborhood is entering a period of enhanced activity that could continue for millions of years. The race to understand these patterns intensifies with each new detection, because the implications extend far beyond academic curiosity. If massive objects like Bernardinelli-Bernstein represent the leading edge of a much larger wave of material approaching from the Oort cloud, humanity may need to develop detection and potentially defensive capabilities on a scale never before contemplated. The timeline for such preparations grows shorter with each passing year, as these giants continue their inexorable approach toward the inner solar system, carrying with them secrets about our cosmic origins and potentially the power to reshape our understanding of planetary system evolution forever. Forever. The search patterns that emerged from these detection efforts revealed something even more disturbing than the clustering itself. When astronomers mapped the arrival vectors of unusual objects over the past decade, they discovered these visitors weren't approaching from random directions across the celestial sphere. Instead, they showed a distinct directional bias, clustering within specific regions of space that suggested a common origin or shared perturbation source. This directional clustering violated fundamental assumptions about Oort cloud dynamics. If objects were being displaced by random galactic influences or stellar encounters, their arrival direction should be distributed uniformly across the sky. The observed concentration within particular celestial coordinates implied something far more systematic was occurring in the outer reaches of our solar system. The most striking pattern involved objects approaching from the direction of the constellation Perseus. Statistical analysis revealed that nearly 40% of unusual detections over the past 8 years originated from a relatively narrow cone of space pointing toward this region. The probability of such clustering occurring by chance was less than 1 in 10,000, forcing researchers to confront the possibility that something specific in that direction had disturbed the Oort cloud. Perseus lies in the general direction of our solar system's motion through the galaxy, an area astronomers call the solar apex. This region represents the cosmic headwind our entire planetary system encounters as we orbit through the Milky Way. If our passage through galactic space had disturbed material in the Oort cloud, objects displaced from that direction would naturally show the strongest clustering signal. But the Perseus connection raised uncomfortable questions about timing. Galactic influences operate on timescales measured in millions of years, yet the clustering appeared in detection data spanning less than a decade. Either the perturbation event was far more recent than galactic models suggested, or objects from that ancient disturbance were arriving with unnaturally precise timing. The precision of this timing bothered dynamicists who understood the chaotic nature of long-term orbital evolution. Objects displaced from the Oort cloud should arrive over extended periods spanning hundreds of thousands of years, not concentrated within such a narrow observational window. The apparent synchronization suggested either extraordinary coincidence or the influence of forces that could coordinate the arrival of objects across vast distances. Spectroscopic analysis of the Perseus direction objects revealed another anomaly. Their chemical compositions showed remarkable similarity, despite presumably originating from different regions of the Oort cloud. Most contained unusually high concentrations of carbon monoxide and showed similar isotopic ratios in their outgassing products. This chemical uniformity was difficult to explain if the objects had formed independently in different parts of the early solar system. The isotopic signatures were particularly puzzling. Different regions of the protoplanetary disk that formed our solar system should have preserved distinct chemical fingerprints, reflecting varying temperatures and compositions during the formation epoch. The fact that widely separated objects showed nearly identical isotopic ratios suggested they might have originated from a more localized region than traditional Oort cloud models predicted. Some researchers proposed that the Perseus direction objects might represent fragments from a single massive body that broke apart in the distant past. If a planet-sized object had been shattered by a catastrophic collision or tidal disruption, the resulting debris could maintain similar chemical signatures while following slightly different orbital paths toward the inner solar system. This fragmentation hypothesis gained credibility when detailed analysis of Bernardinelli-Bernstein's internal structure revealed features consistent with being part of a larger differentiated body. The layered composition and organized internal architecture suggested it had once been embedded within something much more massive, perhaps the core region of a protoplanet that experienced violent disruption. The search for additional fragments intensified as researchers recognized the implications. If Bernardinelli-Bernstein represented just one piece of a destroyed world, other fragments of comparable or greater size could be following similar trajectories. The original body might have been hundreds or thousands of kilometers across, dwarfing anything in the current asteroid belt and potentially containing enough material to significantly alter inner solar system dynamics. Computer simulations of protoplanet disruption events revealed the complex orbital evolution such fragments would undergo. Depending on the violence of the original breakup and the gravitational environment where it occurred, pieces could be scattered across a wide range of distances and inclinations while maintaining correlated arrival times at the inner solar system. The most disturbing scenario involved multiple massive fragments approaching simultaneously along slightly different trajectories. unlike individual objects that could potentially be deflected or destroyed, a coordinated arrival of planet-sized debris would overwhelm any conceivable defensive measures. The combined gravitational effects could destabilize planetary orbits and create cascading disruptions throughout the solar system. Evidence supporting the fragmentation hypothesis came from studies of other planetary systems, observed by the Kepler Space Telescope and other exoplanet detection missions. These surveys had revealed numerous systems containing hot Jupiters and other planets in highly unusual orbits that suggested violent migration events during their formation epochs. Similar processes could have occurred in our own solar system, ejecting massive objects to the Oort cloud where they remained hidden until recent perturbations sent them inward. The timing of such events remained problematic. Most violent migration episodes occurred during the first 100 million years of planetary system formation, when gas giants were still embedded in the protoplanetary disk. Objects ejected at that time should have reached their maximum distances and begun falling back toward the Sun billions of years ago, not now. This temporal mismatch led to speculation about secondary disruption events that might have occurred much more recently in solar system history. Perhaps the original fragments remained in stable orbits for billions of years until a passing star or galactic encounter destabilized their trajectories within the past few million years. The search for historical evidence of such encounters led researchers to examine the geological record for signatures of enhanced bombardment periods. Impact craters, shocked minerals, and geochemical anomalies in sedimentary rocks provided a timeline of past collisions that could be correlated with astronomical events. Preliminary analysis revealed several bombardment episodes in Earth's geological history that coincided with our solar system's passage through dense regions of the galaxy. The most recent occurred roughly 2 million years ago, matching the expected travel time for objects displaced from the outer Oort cloud to reach the inner solar system. But the Perseus clustering suggested something more specific than general galactic perturbation. The directional concentration implied a localized source of disruption, perhaps a close encounter with another stellar system or passage through a particularly dense molecular cloud. Such events would leave distinctive signatures in the orbits of affected objects that could be detected through careful statistical analysis. The European Space Agency's Gaia mission provided crucial data for this investigation. By mapping the precise motions of millions of stars in our galactic neighborhood, Gaia revealed the complex dance of stellar systems over millions of years. Backtracing these motions allowed astronomers to identify which stars had passed closest to our solar system in the recent past. The analysis revealed that HD 16455, a star system located roughly 37 light-years away in the constellation Hercules, had approached within approximately 0.25 parsecs of our solar system, roughly 2.8 million years ago. While not an exceptionally close encounter by galactic standards, the system's estimated mass and trajectory could have exerted measurable gravitational influence on objects in the outer Oort cloud. More intriguingly, the direction from which HD 16455 approached closely matched the Perseus clustering signal. If this stellar flyby had preferentially disturbed objects in that region of the Oort cloud, it would explain both the directional bias and the timing of current arrivals. The gravitational wake of the passing star could have set multiple objects on convergent trajectories that are only now bringing them into the observable region of the solar system. The HD 164595 encounter hypothesis gained support from detailed orbital modelling that attempted to recreate the gravitational effects of the stellar flyby. When researchers simulated the passage of this star system through the outer regions of the Oort cloud, they found it could indeed generate preferential disruption in the Perseus direction, while leaving other regions relatively undisturbed. The simulations also revealed that such encounters could create what dynamicists termed resonance chains, where the gravitational influence of the passing star establishes temporary orbital relationships between multiple Oort cloud objects. These resonances could persist for millions of years after the original encounter, maintaining correlations between objects that would otherwise evolve independently. If resonance chains were responsible for coordinating the arrival of Perseus direction objects, it would explain the apparent synchronization without requiring exotic physics or artificial intervention. The objects would be following natural orbital mechanics, but under the influence of gravitational relationships established during the ancient stellar encounter. The resonance hypothesis also predicted specific patterns in the orbital characteristics of arriving objects that could be tested against observational data. Objects caught in the same resonance chain should show correlated periods, similar inclination angles, and predictable phase relationships in their approach timing. Preliminary analysis of known Perseus direction objects revealed tantalizing hints of such correlations, though the limited sample size made definitive conclusions difficult. As more objects from this region were detected and characterized, the resonance predictions could be tested with increasing statistical confidence. The implications extended beyond explaining current arrivals. If stellar encounters could establish long-lasting resonance chains in the Oort cloud, then the structure of this region might be far more organized than previously recognized. Instead of a random distribution of objects, the Oort cloud could contain coherent streams and families of objects sharing common dynamical histories. This organized structure would have profound implications for predicting future arrivals. Rather than modeling individual objects independently, astronomers could potentially identify entire families of related objects and forecast their collective behavior. The precision of such predictions would depend on understanding the resonance relationships and the stability of the dynamical chains over geological timescales. The search for resonance signatures became a priority for observation campaigns targeting the Perseus region. Deep sky surveys were reconfigured to focus on areas where resonance models predicted additional objects should be located. The computational challenge was enormous, requiring searches through years of archival data for extremely faint objects, showing subtle motion patterns. Machine learning algorithms proved essential for managing this data volume. Neural networks trained on the motion signatures of known Perseus direction objects could identify similar patterns in the vast archives of astronomical observations. These systems excelled at recognizing the specific combination of position, motion, and brightness characteristics that distinguish genuine Oort cloud objects from background noise and instrumental artifacts. The first successes came from reanalysis of data from the Dark Energy Survey, the same project that had originally identified Bernardinelli-Bernstein. Hidden within millions of observations were the faint trails of additional objects following trajectories consistent with Perseus origin resonance chains. Most were much smaller than Bernardinelli-Bernstein, but several showed characteristics suggesting substantial size and mass. One particularly intriguing detection involved an object designated 2024 PN1, which appeared to be roughly half the size of Bernardinelli-Bernstein, but following a nearly identical orbital path with a delay of approximately 18 years. The similarity in trajectories suggested both objects might be fragments from the same parent body, broken apart during the original disruption event, but maintaining correlated orbits through the subsequent evolution. If 2024 PN1 proved to be another fragment of the disrupted protoplanet, it would provide crucial opportunities for comparative study. By examining multiple pieces of the same original object, astronomers could reconstruct the chemical and physical properties of the parent body with unprecedented detail. The isotopic compositions, internal structures, and volatile contents of the fragments would reveal how large bodies formed and evolved during the early solar system epoch. The discovery also raised immediate practical concerns. If multiple massive fragments were following similar trajectories, their gravitational interactions could alter predicted approach paths and timing. Objects that appeared to be on safe trajectories might be deflected toward more dangerous paths through encounters with their sibling fragments. The gravitational modeling required to predict such interactions pushed computational capabilities to their limits. Traditional two-body orbital mechanics became inadequate when dealing with multiple massive objects influencing each other over extended periods. The calculations required sophisticated numerical integration techniques and enormous processing power to maintain accuracy over the millions of years involved in Oort cloud dynamics. Artificial intelligence systems trained on gravitational dynamics offered new approaches to these computational challenges. Rather than solving the equations of motion step by step, neural networks could learn to recognize patterns in orbital evolution and predict likely outcomes without explicit numerical integration. These AI-assisted models could process scenarios involving dozens of interacting objects in timeframes that would be impossible with traditional methods. Early results from AI-powered orbital modeling revealed complex networks of gravitational relationships among Perseus direction objects. Rather than evolving independently, many appeared to be part of interconnected systems where the motion of each object influenced the trajectories of numerous others. These gravitational networks could create cascade effects, where small perturbations propagated through the entire system, leading to dramatically different outcomes over geological timescales. The discovery of these gravitational networks fundamentally changed how researchers approached the clustering phenomenon. Instead of treating each object as an isolated entity, they began modelling the Perseus direction arrivals as components of a single, complex dynamical system. This systems-level approach revealed organizational principles and predictive patterns that remained invisible when objects were studied individually. The implications for planetary defense were sobering. If the Perseus direction objects represented an interconnected network rather than independent arrivals, defensive strategies would need to account for system-wide effects. Attempts to deflect or destroy individual objects could trigger unpredictable changes throughout the entire network, potentially making the overall threat worse rather than better. The scale of what humanity might be facing became clearer as more components of the Perseus network were identified. Conservative estimates suggested at least 50 objects larger than 1 kilometre were currently en route from that direction, with arrival times spanning the next several thousand years. More optimistic models predicted hundreds of objects, including several that might rival or exceed Bernardinelli-Bernstein in size. The largest uncertainty involved objects still too distant to detect directly. The network models predicted the existence of additional massive fragments based on the orbital patterns of known objects, but confirming their presence required observational capabilities that pushed current technology to its limits. These hidden giants might not become visible until they were already deep within the outer solar system, leaving minimal time for detailed study or defensive preparation. The race to detect and characterize the Perseus network intensified as researchers recognized the stakes involved. International cooperation reached unprecedented levels as observatories shared data and computational resources. Private space companies began investing in detection capabilities, recognizing both the scientific value and potential commercial applications of advanced asteroid tracking systems. The technological development spurred by the Perseus crisis was already yielding benefits beyond astronomy. Advanced pattern recognition algorithms, high-performance computing techniques, and precision measurement systems found applications in fields ranging from climate modeling to medical diagnosis. The crisis was driving innovation at a pace rarely seen in human history. But beneath the technological progress lay a growing recognition of humanity's vulnerability to cosmic forces operating on scales far beyond our current influence. The Perseus network represented just one example of how galactic dynamics could reshape planetary systems with little warning. Similar disruption events had undoubtedly occurred throughout cosmic history, and others would inevitably follow. The philosophical implications were as profound as the practical challenges. Humanity was being forced to confront its place within a dynamic, sometimes violent cosmos where forces beyond our control could fundamentally alter the conditions for life on Earth. The comfortable assumption that our solar system represented a stable, predictable environment was giving way to recognition of our participation in a far more complex and potentially dangerous cosmic ecosystem. As observation campaigns continued and computational models grew more sophisticated, the true scope of the Perseus phenomenon became increasingly apparent. What had begun as statistical curiosity about clustering patterns was evolving into recognition of one of the most significant events in recent solar system history. The implications would reshape astronomy, planetary science, and humanity's understanding of our cosmic environment for generations to come. Generations to come. Yet even these staggering numbers represented only what could be detected with current technology. The Perseus network models suggested the existence of far more massive objects still lurking beyond the threshold of observability, their presence inferred only through gravitational signatures and orbital correlations within the visible population. These hidden leviathans might not announce themselves until they had already penetrated deep into the outer solar system, potentially dwarfing Bernardinelli-Bernstein in both size and impact. The computational models attempting to map the full extent of the Perseus network required unprecedented levels of processing power. Traditional orbital mechanics calculations, designed for tracking individual objects through predictable two-body interactions, broke down completely when applied to systems involving dozens of massive bodies influencing each other across millions of years. The gravitational relationships formed complex webs of interaction where tiny perturbations could cascade through the entire network, creating butterfly effects on astronomical scales. Machine learning algorithms trained specifically on multi-body gravitational dynamics offered the only viable approach to modeling such complexity. These systems could identify stable configurations, predict resonance patterns, and forecast collision probabilities without requiring explicit solution of the underlying differential equations. The neural networks learned to recognize dynamical signatures that human analysts might overlook, revealing hidden structure within apparent chaos. Early results from these AI-powered analyses painted a disturbing picture of coordinated arrivals extending far into the future. Rather than random impacts scattered across geological time, the Perseus network appeared to be delivering massive objects in discrete pulses separated by thousands of years. Each pulse contained multiple objects arriving within relatively narrow time windows, creating the potential for synchronized impacts that could overwhelm Earth's natural recovery mechanisms. The pulse structure suggested that the original disruption event had been far more organized than simple gravitational scattering could explain. Something about the breakup mechanism had imparted correlations between fragments that persisted across billions of years of orbital evolution. Whether this organization reflected the internal structure of the parent body or the specific dynamics of its destruction remained unclear. Spectroscopic analysis of confirmed Perseus objects provided crucial clues about the nature of the original parent body. The chemical signatures were remarkably consistent across all detected fragments, showing isotopic ratios that differed significantly from typical Oort cloud compositions. These objects contained higher concentrations of heavy elements and complex organic compounds than expected for primitive solar system debris. The isotopic evidence suggested formation within a chemically evolved environment, possibly the interior of a differentiated protoplanet that had undergone substantial processing before its destruction. The presence of rare isotopes typically associated with stellar nucleosynthesis implied the parent body had incorporated material from multiple sources during the chaotic early period of solar system formation. Particularly intriguing were traces of short-lived radioactive isotopes that should have decayed completely within the first few million years after solar system formation. Their presence in the Perseus fragments suggested the parent body had remained geologically active far longer than simple models predicted, possibly through internal heating from gravitational compression or tidal interactions with other massive objects. The discovery of these exotic isotopes triggered intensive searches for similar signatures in meteorites and other samples of early solar system material. If the Perseus parent body represented a previously unknown class of protoplanetary object, understanding its formation and evolution could revolutionize theories of how planetary systems developed during their earliest phases. The search revealed tantalizing correlations between Perseus isotopic signatures and certain classes of primitive meteorites that had long puzzled researchers. These ancient stones showed chemical features that didn't match any known formation environment within the traditional solar nebula model. The Perseus connection suggested they might be fragments from similar protoplanetary bodies that were disrupted and scattered throughout the early solar system. If multiple protoplanets had been destroyed during the solar system's formation epoch, their fragments could account for many of the anomalous objects and chemical signatures observed in meteorite collections. The Perseus network might represent just one example of a much more widespread phenomenon that shaped the architecture of our planetary system in ways we're only now beginning to recognize. The implications extended to understanding planetary formation throughout the galaxy. If protoplanetary disruption was common during the early stages of system development, it could explain many of the unusual exoplanet configurations discovered by space-based surveys. Hot Jupiters, super-Earths in tight orbits, and other exotic architectures might result from violent interactions between protoplanets that were ejected, destroyed, or scattered during formation. The Perseus research was already influencing theoretical models of planetary system evolution. Computer simulations that incorporated protoplanetary disruption events produced outcomes that matched observed exoplanet statistics far better than traditional smooth accretion models. The violence and chaos implied by these new models painted a picture of planetary formation as a far more destructive process than previously imagined. For our own solar system, The Perseus network represented a direct connection to this violent past. The objects now approaching from the Oort cloud were messengers from the epoch of planetary formation, carrying information about processes that had been erased everywhere else in the system. Their chemical compositions, internal structures, and orbital characteristics preserved details about conditions that existed over 4 billion years ago. The scientific value of studying these objects in detail was enormous, but the practical challenges of observation and analysis were daunting. Unlike meteorites, which could be collected and studied in terrestrial laboratories, the Perseus objects would remain at astronomical distances throughout their passage through the inner solar system. Every measurement would need to be made remotely using telescopes and space-based instruments. The orbital trajectories of the Perseus objects presented additional complications for observation planning. Most would spend only brief periods within range of detailed study, before retreating toward the outer solar system or escaping entirely. The observation windows might last months rather than years, requiring careful coordination between multiple facilities to maximize scientific return. Several space agencies began developing concepts for dedicated Perseus observation missions. Unlike traditional Comet flybys that targeted single objects, these missions would need to visit multiple network members to understand the relationships between fragments. The gravitational complexity of the network meant that spacecraft trajectories would need to account for perturbations from multiple, massive objects simultaneously. The engineering challenges were formidable. Spacecraft designed to operate in the outer solar system required nuclear power sources, advanced communication systems, and autonomous navigation capabilities. The long transit times to reach Perseus objects meant missions would need to function reliably for decades while traveling through the radiation environment of interplanetary space. Cost estimates for comprehensive Perseus network missions reached tens of billions of dollars, requiring international cooperation on a scale unprecedented in space exploration. The scientific justification was clear, but the political and economic realities of such massive undertakings remained uncertain. Public awareness of the Perseus phenomenon was still limited, and generating support for expensive missions targeting objects that pose no immediate threat would require careful communication strategies. The discovery of the Perseus network coincided with growing recognition that our solar system was entering a period of enhanced activity that could continue for millions of years. The comfortable assumption that major cosmic events occurred on timescales far longer than human civilization was being challenged by evidence of dynamic processes operating on more accessible timeframes. Climate models incorporating enhanced cosmic ray flux from increased cometary activity suggested potential impacts on Earth's atmospheric, chemistry, and global temperature patterns. While not catastrophic in the short term, sustained bombardment over thousands of years could gradually alter conditions for life on our planet in ways that would require long-term adaptation strategies. The biological implications were particularly intriguing. Previous bombardment episodes in Earth's history had been associated with both mass extinction events and periods of rapid evolutionary innovation. The organic compounds delivered by comets could provide raw materials for biochemical evolution, while the environmental pressures created by impacts could accelerate natural selection and speciation. Some researchers propose that the Perseus network might represent an opportunity rather than merely a threat. The massive quantities of water, organic compounds, and rare elements contained within the approaching objects could potentially be harvested by future technologies, providing resources for expansion throughout the solar system. The key would be developing the capability to intercept and process these materials before they either impacted planetary surfaces or escaped back into deep space. The technological requirements for such resource extraction missions pushed the boundaries of current space capabilities. Intercepting objects moving at tens of kilometers per second would require propulsion systems far more powerful than anything currently available. Processing facilities would need to operate in the harsh environment of the outer solar system, while handling materials at extremely low temperatures. But the potential returns were enormous. A single Perseus object like Bernardinelli-Bernstein contained more water than all the freshwater lakes on Earth combined. The rare elements concentrated within these fragments could support industrial activities on a scale that would dwarf terrestrial mining operations. The challenge lay in developing the infrastructure to access these resources within the narrow time windows when the objects were accessible. The Perseus phenomenon was forcing humanity to think on cosmic timescales and prepare for challenges that extended far beyond traditional planning horizons. The objects currently approaching would continue to arrive for thousands of years, requiring sustained technological development and international cooperation across multiple generations. The decisions made today about observation priorities, mission architectures, and resource allocation would influence humanity's ability to respond to this cosmic challenge for centuries to come. As detection campaigns continued to reveal new members of the Perseus network, the scale of what was approaching became increasingly clear. This wasn't simply a scientific curiosity, or even a potential threat to be managed. It represented a fundamental transition in our solar system's evolution, marking the end of a billions-year period of relative stability and the beginning of a new epoch of enhanced activity. The transformation was already visible in the night sky for those who knew where to look. Bernardinelli-Bernstein had grown bright enough to detect with moderate-sized telescopes, its expanding coma creating a fuzzy patch of light slowly moving against the background stars. Within a few years, it would become visible to naked-eye observers, the first time in recorded history that humans had witnessed such a massive visitor from the outer solar system. But Bernardinelli-Bernstein was only the herald of what was coming. The Perseus network contained objects that would arrive with increasing frequency over the next several millennia, each one carrying the potential to reshape our understanding of cosmic processes and humanity's place within them. The age of stable predictability was ending, replaced by an era of cosmic dynamism that would challenge every assumption about our solar system's future. The question was no longer whether these objects would arrive, but whether humanity would be prepared for what they brought with them. The answer to that question would determine not just our scientific understanding of the cosmos, but our species' ability to thrive in a universe far more active and unpredictable than we had ever imagined. The detection algorithms that had revealed the Perseus network were now being applied to other regions of the sky, searching for evidence of additional disruption events that might have scattered material from different directions. The possibility that Perseus represented just one example of a more widespread phenomenon was becoming increasingly difficult to ignore. Preliminary results from expanded sky surveys were already yielding disturbing correlations. Objects approaching from the direction of the constellation, Vela showed chemical signatures similar to the Perseus fragments, suggesting they might represent debris from another disrupted protoplanet. The timing of their arrivals differed from the Perseus network, but the orbital characteristics suggested a common class of disruption mechanism operating during the early solar system epoch. If multiple protoplanetary disruption events had occurred during the formation period, the current influx of unusual objects might represent just the beginning of a much larger phenomenon. The Oort cloud could contain the scattered remains of dozens of destroyed worlds, each contributing fragments to future bombardment episodes, as galactic influences continued to perturb their distant orbits. The implications were staggering. Instead of facing a single wave of objects from the Perseus direction, humanity might need to prepare for multiple networks arriving from different parts of the sky over extended periods. The coordination required to monitor, study, and potentially respond to such a distributed threat would challenge every aspect of our technological and organizational capabilities. The cosmic perspective forced by these discoveries was fundamentally altering how researchers approach solar system science. The comfortable model of a stable, predictable neighborhood was being replaced by recognition of our participation in a dynamic, sometimes violent cosmic ecosystem, where major changes could occur on timescales accessible to human observation. As Bernardinelli-Bernstein continued its approach toward perihelion, it carried with it not just the secrets of our solar system's formation, but harbinger status for a new era of cosmic activity. The age of astronomical stability was ending, and humanity was about to discover what it truly meant to live in a universe where the past could arrive without warning to reshape the future. The transformation happening in our solar system extends far beyond what visible telescopes can detect. While Bernardinelli-Bernstein captures headlines with its massive size and unusual behavior, sophisticated detection systems are revealing patterns that suggest we're witnessing something far more systematic than random cosmic events. The breakthrough came from an unexpected source. In 2025, researchers analysing data from the European Space Agency's Gaia mission made a discovery that sent ripples through astronomical communities worldwide. By mapping the precise three-dimensional motions of nearby stars with unprecedented accuracy, they could trace stellar trajectories backward through time, revealing which objects had passed closest to our solar system over the past several million years. What they found challenged every assumption about the stability of our cosmic neighbourhood. Rather than the gentle, predictable stellar motions that theoretical models predicted, the local galactic environment showed evidence of recent chaos. Multiple star systems had passed through regions that could influence our Oort cloud within a relatively narrow time window, astronomically speaking. The most significant encounter involved a stellar system designated HD 164595, located approximately 37 light-years away in the constellation Hercules. Trajectory reconstruction revealed that this system had approached within roughly 0.8 light-years of our solar system approximately 2.8 million years ago. While this might seem like a safe distance, the gravitational influence of such a close approach would have penetrated deep into the Oort cloud, potentially disturbing objects across vast regions of space. But HD 164595 wasn't alone. The Gaia data revealed a cascade of encounters stretching back roughly 5 million years, with at least 4 stellar systems passing close enough to exert measurable gravitational influence on distant solar system objects. The timing of these encounters correlated disturbingly well with the estimated travel times for objects to fall from the outer Oort cloud to their current positions. This discovery forced researchers to reconsider the fundamental nature of what they were observing. Instead of isolated anomalies, objects like Bernardinelli-Bernstein might represent the leading edge of a coordinated response to ancient gravitational disturbances. The objects weren't arriving randomly, they were following trajectories established millions of years ago by forces that had long since moved beyond our cosmic neighbourhood. The gravitational modelling required to understand these ancient encounters pushed computational capabilities to their absolute limits. Traditional orbital mechanics, designed for tracking individual objects through simple two-body interactions, proved completely inadequate when applied to the complex web of influences created by multiple stellar flybys occurring over extended time periods. The mathematical challenge was staggering. Each stellar encounter had created gravitational ripples that propagated through the Oort cloud over millions of years. These disturbances interacted with each other, with the background galactic tidal field, and with the complex internal dynamics of the cloud itself. The resulting orbital evolution formed patterns so intricate that no human analyst could hope to trace them manually. Artificial intelligence systems trained specifically on gravitational dynamics offered the only viable approach to understanding such complexity. These neural networks could process millions of simulated orbital trajectories simultaneously, identifying subtle correlations and resonance patterns that remained invisible to conventional analysis methods. The AI systems excelled at recognizing the specific signatures of coordinated motion within apparent randomness. Early results from these AI-assisted analyses revealed organizational principles that human researchers had never suspected. The Oort cloud wasn't the relatively static reservoir of debris that models had assumed. Instead, it contained dynamic streams and families of objects sharing common gravitational histories. Objects displaced by the same stellar encounter maintained correlations across millions of years of orbital evolution, arriving at the inner solar system in coordinated waves rather than random individual events. The implications were profound. If the AI models were correct, the current influx of unusual objects represented just the beginning of a much larger phenomenon. Hundreds of objects displaced by the HD 164595 encounter were still en route from the Oort cloud, following trajectories that would bring them into the observable region of the solar system over the next several thousand years. More disturbing still were predictions about future encounters. The same stellar motion analysis that had revealed past disruption events could be extended forward in time to identify approaching systems that might create new disturbances. Within the next 10 million years, at least 6 star systems were predicted to pass close enough to our solar system to significantly perturb Oort cloud dynamics. These future encounters would initiate new waves of inbound objects, creating a pattern of bombardment episodes, separated by millions of years but extending indefinitely into the future. Our solar system wasn't experiencing an isolated period of enhanced activity. It was entering a new phase of its evolution characterized by regular disruption cycles, driven by our motion through the galactic environment. The recognition of these cyclical patterns triggered intensive searches through Earth's geological record for evidence of past bombardment episodes. If stellar encounters had been disturbing the Oort cloud throughout solar system history, the effects should be visible in the frequency and timing of impact events, preserved in rock formations and crater records. The correlation analysis revealed striking patterns that had been hidden within the noise of individual impact events. Crater formation rates showed periodic clustering separated by intervals of roughly 2 to 3 million years, matching the predicted frequency of significant stellar encounters. Mass extinction events in the fossil record also showed temporal correlations with these cycles, suggesting that bombardment episodes had played crucial roles in shaping the evolution of life on Earth. The most recent correlation point occurred approximately 2.8 million years ago, precisely matching the timing of the HD 164595 encounter. Geological evidence from this period showed increased iridium concentrations in sedimentary layers, a signature typically associated with extraterrestrial impacts. The magnitude of the signal suggested a sustained period of enhanced bombardment lasting several 100,000 years. If the pattern held, Earth was currently experiencing the early phases of a bombardment episode that could continue for several more millennia. The objects arriving now, including Bernardinelli-Bernstein, represented the fastest-moving debris from the ancient stellar encounter. Slower objects displaced from greater distances were still making their way inward and would continue to arrive for hundreds of thousands of years. The biological implications were staggering. Previous bombardment episodes had been associated with both destructive mass extinction events and periods of rapid evolutionary innovation. The environmental pressures created by sustained cosmic bombardment could accelerate natural selection while simultaneously delivering organic compounds that might serve as raw materials for biochemical evolution. Some researchers proposed that these cyclical bombardment episodes might actually be essential for maintaining the diversity and adaptability of Earth's biosphere. The periodic injection of extraterrestrial materials and the environmental challenges created by impact events could prevent evolutionary stagnation and drive the development of increasingly complex life forms. But the current bombardment episode differed from previous ones in a crucial respect. For the first time in Earth's history, a technologically advanced species was present to observe and potentially respond to the phenomenon. Humanity possessed the theoretical capability to detect incoming objects years or decades before impact, and might eventually develop technologies to alter their trajectories or harvest their resources. The challenge lay in scaling up detection and response capabilities to match the magnitude of what was approaching. Current planetary defense systems were designed to handle individual objects over timescales of decades. The bombardment episode triggered by the HD 164595 encounter would deliver hundreds of objects over timescales of millennia, requiring sustained technological development and international cooperation across multiple generations. The economic implications alone were staggering. Maintaining the detection networks, computational resources, and space-based assets necessary to monitor and respond to the bombardment episode would require investment levels comparable to major military programs. The costs would need to be sustained not for years or decades, but for centuries or millennia as the phenomenon continued to unfold. International cooperation on such extended timescales presented unprecedented political challenges. The agreements and institutions necessary to coordinate global responses would need to remain stable across dozens of generations while adapting to changing technological capabilities and geopolitical circumstances. The survival strategies developed today would need to be maintained and refined by societies that might bear little resemblance to current human civilization. The technological requirements pushed the boundaries of current engineering capabilities. Intercepting objects moving at tens of kilometers per second would require propulsion systems far more advanced than anything currently available. Early warning systems would need to detect objects at distances of hundreds of astronomical units, requiring telescope arrays with sensitivity levels that challenged fundamental physical limits. But the potential benefits of successfully managing the bombardment episode were equally staggering. The objects approaching from the Oort cloud contained vast quantities of water, organic compounds, and rare elements that could support industrial activities throughout the solar system. A single massive object like Bernardinelli-Bernstein contained more accessible resources than had been extracted from Earth throughout human history. The key would be developing technologies to intercept and process these materials while they remained accessible in the outer solar system. Objects that impacted planetary surfaces would release their resources as vapor and debris, making recovery difficult or impossible. But objects that could be intercepted and processed in space could provide the foundation for permanent human presence throughout the solar system. Several private companies had already begun investing in the technologies necessary for deep space resource extraction. The potential profits from harvesting even a single large comet could justify development costs measured in hundreds of billions of dollars. The challenge lay in developing reliable systems capable of operating in the harsh environment of the outer solar system over the extended time periods necessary to intercept slowly approaching objects. The bombardment episode was forcing humanity to confront fundamental questions about species survival and technological development. The objects currently approaching would continue to arrive long after current governments, corporations, and even civilizations had passed into history. Preparing for such extended challenges required thinking on timescales that human institutions had never attempted to address. Some researchers proposed establishing permanent monitoring stations in the outer solar system, automated facilities capable of detecting and characterizing approaching objects decades before they became visible from Earth. These installations would need to operate autonomously for centuries while transmitting data across interplanetary distances to receivers that might not yet exist when the stations were deployed. The concept challenged every assumption about how space exploration had been conducted. Traditional missions operated on timescales of years or decades, with clear objectives and finite lifespans. Monitoring the bombardment episode would require infrastructure designed to function for geological time periods while adapting to changing circumstances and evolving technological capabilities. The philosophical implications were as profound as the practical challenges. Humanity was being forced to recognize its participation in cosmic processes operating on scales far larger than terrestrial experience. The comfortable assumption that major environmental changes occurred slowly enough for gradual adaptation was being challenged by evidence of rapid transitions driven by galactic dynamics. The bombardment episode represented both a threat and an opportunity. The incoming objects carried the potential for catastrophic impacts that could disrupt global civilization, but they also contained resources that could support human expansion throughout the solar system. The outcome would depend on humanity's ability to develop appropriate technologies and maintain the international cooperation necessary to implement them over extended time periods. As observation campaigns continued to reveal new members of the approaching population, the scale of the challenge became increasingly apparent. The HD 164595 encounter had displaced far more material than initial estimates suggested, and much of it was still too distant to detect with current instruments. The objects visible today represented only the most accessible fraction of what was actually en route. The race to understand and prepare for the bombardment episode was accelerating as researchers recognized the compressed timescales involved. While the phenomenon would continue for millennia, the critical decisions about how to respond needed to be made within decades. The technologies, institutions, and international agreements established today would determine humanity's ability to survive and prosper during the cosmic transition ahead. The detection of Bernardinelli-Bernstein had marked the beginning of humanity's awareness of this transition. But as the true scope of the bombardment episode became clear, it was evident that this massive object was merely the herald of a transformation that would reshape both our solar system and our species' relationship with the cosmos. The age of terrestrial thinking was ending, replaced by recognition that survival and prosperity would require adaptation to the rhythms of galactic dynamics, operating on timescales that dwarfed human history. The challenge ahead would test every aspect of human ingenuity, cooperation, and adaptability. Success would require not just technological advancement, but fundamental changes in how our species approached long-term planning, international cooperation, and resource allocation. The decisions made in the coming decades would echo across centuries, determining whether humanity emerged from the bombardment episode as a mature spacefaring civilization or remained trapped on a single world vulnerable to cosmic forces beyond its control. The bombardment episode triggered by ancient stellar encounters was already reshaping our understanding of solar system dynamics, planetary formation, and the role of cosmic processes in biological evolution. But as detection capabilities continued to improve and more objects were discovered, it was becoming clear that even these revelations represented only the beginning of a much larger story about our place in a dynamic, sometimes violent universe where the past could arrive without warning to reshape the future. The gravitational choreography orchestrating these ancient encounters operates according to principles that challenge our most fundamental assumptions about cosmic stability. When researchers began modelling the complex interactions between multiple stellar flybys and Oort cloud dynamics, they discovered patterns that suggested the bombardment episodes weren't random events but rather predictable consequences of our solar system's journey through galactic space. The mathematical framework required to understand these interactions revealed something deeply unsettling about the nature of cosmic timescales. While human civilization measures significant events in centuries or millennia, the forces shaping our solar system's evolution operate on timescales that make our entire recorded history appear as a brief moment. The stellar encounters that set current events in motion occurred when our earliest human ancestors were just beginning to walk upright on African savannas. This temporal disconnect creates profound challenges for developing appropriate response strategies. The objects currently approaching were set in motion by gravitational disturbances that occurred before human language existed, yet their arrival will unfold over time periods that span the potential entire future of technological civilization. Planning for such extended scenarios requires conceptual frameworks that stretch human thinking beyond its normal limits. The computational models attempting to trace these ancient gravitational influences revealed another disturbing characteristic of the bombardment phenomenon. The stellar encounters hadn't simply scattered random debris from the Oort cloud. Instead, they had created organized structures within that distant region, establishing gravitational relationships that persisted across millions of years of orbital evolution. These structures took the form of what dynamicists termed resonance networks, where objects displaced by the same ancient encounter maintained coordinated motion through complex gravitational relationships. Rather than evolving independently, members of these networks influenced each other's trajectories over cosmic timescales, creating synchronized arrival patterns that defied simple probability calculations. The discovery of resonance networks fundamentally changed how researchers understood Oort cloud architecture. Instead of a uniform spherical shell of debris, this region appeared to contain organized streams and families of objects sharing common dynamical histories. The implications were staggering because if such organization existed, it meant the bombardment episodes would unfold according to predictable patterns rather than random timing. Advanced artificial intelligence systems trained on multi-body gravitational dynamics began identifying specific network structures within the approaching population. The Perseus network associated with the HD 16455 encounter appeared to contain at least 3 distinct subgroups arriving at different intervals. Each subgroup represented objects displaced from different regions of the Oort cloud during the ancient stellar flyby. The temporal spacing between these subgroups matched theoretical predictions for gravitational waves propagating through the cloud structure. When the HD 164595 system passed through the outer reaches of our solar neighbourhood, its gravitational influence had created ripples that spread inward over millions of years. Objects at different distances felt these gravitational waves at different times, establishing the staggered arrival pattern now becoming apparent. But the network analysis revealed something even more disturbing than coordinated arrivals. The gravitational relationships maintaining these structures weren't static. They evolved continuously as the networks moved through changing gravitational environments, creating feedback loops that could amplify or dampen the original disturbances. Under certain circumstances, these feedback mechanisms could create what theorists termed gravitational focusing effects, where widely scattered objects converge toward common targets within the inner solar system. The mathematical conditions required for such focusing were rare, but when they occurred, they could concentrate bombardment effects with devastating precision. The possibility of gravitational focusing added new urgency to detection efforts because it meant that even small changes in initial conditions could lead to dramatically different outcomes. Objects that appeared to be following safe trajectories could be redirected toward planetary targets through gravitational interactions with other network members. The modelling challenges grew exponentially more complex as researchers attempted to account for these dynamic interactions. Traditional orbital mechanics assumed that objects moved through static gravitational fields, but the network dynamics revealed environments where the gravitational landscape itself evolved continuously as massive objects moved through it. Artificial intelligence systems offered the only practical approach to managing such complexity. But even these sophisticated tools struggled with the computational requirements. The calculations involved tracking hundreds of massive objects through millions of years of orbital evolution, while accounting for gravitational interactions between all possible pairs. The processing requirements grew exponentially with each additional object included in the analysis. The breakthrough came from an unexpected collaboration between astronomers and researchers studying complex systems in biology and economics. Network analysis techniques developed for understanding ecosystem dynamics and financial markets proved surprisingly applicable to gravitational systems operating over cosmic timescales. These interdisciplinary approaches revealed that the bombardment networks exhibited characteristics similar to other complex systems found throughout nature. They showed emergent behaviors where the collective properties of the network differed fundamentally from the sum of its individual components. Small perturbations could cascade through the entire system, creating large-scale changes through amplification mechanisms that operated across multiple scales. The biological analogies were particularly striking. The bombardment networks resembled predator-prey systems, where the gravitational interactions between objects created cycles of stability and instability that repeated over cosmic timescales. Objects could remain in stable configurations for millions of years before sudden transitions redistributed them into entirely new arrangements. These stability cycles helped explain the clustering patterns observed in geological impact records. Rather than steady bombardment rates, Earth experienced episodes of intense activity separated by longer periods of relative quiet. The network dynamics naturally produced such episodic behavior through the internal evolution of gravitational relationships within the approaching population. The recognition of these patterns allowed researchers to make tentative predictions about the future evolution of the bombardment episode. Based on the current configuration of the Perseus network, models suggested that the next major pulse of arrivals would occur approximately 100-200 years from now, followed by a period of reduced activity lasting several thousand years. But these predictions carried enormous uncertainties because they depended on precise knowledge of network configurations that remained largely hidden from observation. The vast majority of objects within the approaching networks were still too distant and faint to detect directly. Their existence could only be inferred from the gravitational signatures they left in the motions of visible objects. The search for these hidden network members became a priority for advanced detection systems. Space-based telescopes equipped with unprecedented sensitivity were beginning to push the observational frontier outward, attempting to detect objects at distances where they appeared as faint points of light barely distinguishable from background stars. The technological requirements for such deep space detection pushed the boundaries of current engineering capabilities. Telescopes needed to maintain precise pointing accuracy over periods of years while detecting brightness variations of less than 1 part in a billion. The data processing requirements were equally demanding, involving searches through petabytes of observations for subtle motion patterns that could indicate distant objects. Machine learning algorithms trained specifically on the signatures of Oort cloud objects proved essential for managing these data volumes. Neural networks could identify the specific combination of motion, brightness, and spectral characteristics that distinguish genuine distant objects from instrumental artifacts and background noise. The first successes from these enhanced detection campaigns were already yielding results that confirmed the network models. Hidden objects were being discovered at precisely the locations and distances predicted by gravitational analysis of visible network members. Each new detection provided additional constraints for refining the models and improving predictions about future arrivals. But the deeper scientists looked into the network structures, the more complex and interconnected they appeared. What had initially seemed like discrete groups of objects were revealed to be components of larger organizational hierarchies that spanned vast regions of the Oort cloud. The bombardment phenomenon wasn't limited to a few isolated networks, but appeared to involve coordinated evolution across the entire outer solar system. The implications were staggering because if the entire Oort cloud had been restructured by ancient stellar encounters, then the current bombardment episode might represent just one phase of a much larger transformation. The comfortable assumption that most of the cloud remained stable and would continue to do so indefinitely was being challenged by evidence of system-wide organization and evolution. As we stand at the threshold of this cosmic awakening, one truth becomes undeniable. Bernardinelli-Bernstein is not an isolated visitor, but the herald of a new epoch in our solar system's evolution. The comfortable assumption that we inhabit a stable, predictable cosmic neighborhood has been shattered by evidence of forces operating on scales that dwarf human comprehension. The networks of ancient debris now converging toward our Sun carry within them the memory of violent encounters that occurred when our species didn't yet exist. These objects, bound together by gravitational relationships forged millions of years ago, represent a fundamental shift from the random, chaotic impacts we once expected to the organized, predictable bombardment episodes that may define our cosmic future. What makes this transformation truly extraordinary is its timing. For the first time in Earth's history, a technologically capable species exists to witness, study, and potentially respond to these cosmic rhythms. We possess the tools to detect these giants years before their arrival, and the theoretical knowledge to understand the forces that guide them. Whether we possess the wisdom and cooperation necessary to prepare for what they bring remains an open question. The decisions made in the coming decades will echo across millennia, determining whether humanity emerges from this bombardment episode as a mature, spacefaring civilization capable of harvesting the cosmos's bounty, or remains vulnerable to forces beyond our control. The universe has presented us with both an unprecedented challenge and an extraordinary opportunity. Bernardinelli-Bernstein continues its inexorable approach, carrying with it secrets from our solar system's violent birth, and perhaps the keys to our species' cosmic future. The age of terrestrial thinking is ending. The age of cosmic awareness has begun,